In this video, we want to discuss about the complexity analysis of algorithm. Once we design an algorithm, next step is to analyze it to see whether that will be an effective algorithm in order to transform it to a program or not. So in order to analyze that algorithm, we need to analyze the complexity. Basically, the complexity of an algorithm, it gives a measure of time and the space required to complete the algorithm for a given input size. And while analyzing the complexity of the algorithm, we take into account two things. One is the time, another is the space, time and space. By the time, by the word time, we does not mean necessarily the time in terms of minutes, seconds or milliseconds. Rather, what we say by the term time, we mean the required CPU cycles. CPU cycles. For example, if we have a statement like A is equals to 7, it's an assignment statement. Another statement B, which is equals to C, or say A plus some value 8. So these statements, it is assumed that it takes one CPU cycle, one cycle or one unit time to complete by the computer. Similarly, this one also takes one cycle. That's why altogether it takes two cycles or 2 unit time to complete these two tasks. But if I give a loop here, suppose I give one loop, I is equals to 1 till n, then if I write these two statements within a loop, this becomes a loop now. Now the times required to complete this loop depends upon the value of n. This time required here, we can write down the time required to execute this code segment is proportional, directly proportional to n. If I say that this time is y, then y is a function of n. And as n grows, the function y or value of y will also grow. So that is the measure of time complexity of any algorithm. In order to analyze the time complexity of the algorithm, we have to analyze the entire algorithm. We have to look for those loops available. We have to look for function calls or recursive function calls. Altogether, we have to come with a conclusion of y, where y is a time required. Y is the time required to complete that function or that algorithm, and that should be in terms of n, which is where n is the size of the input. That is why it is said that it is a measure of time in terms of number of cycles required, and that time required is dependent primarily on the size of the input. Similarly, we also can analyze that algorithm in terms of space required. Here the space is required, it is very obvious that when we write an algorithm, we keep in mind one thing, that we will have some input, that input will have some size and it will produce some output. Now the size, depending upon the size of the input n, if suppose n is say 100 and type of data we want to process is say integer, one integer data may take say 6 bytes, that means 6 into 100 total equals to 600 bytes will be required for storing the entire data, so storing the data in while executing that algorithm. So here it is that here it is said that the time, both time and space complexity is calculated asymptotically. Asymptotically means that the function, that quantity time is a function of some input or some other dependent variable. Here the dependent variable is the size of data. So that's why it is called that calculation of time or the space in complexity analysis is done done asymptotically. So there are certain notations in order to calculate the time complexity of any algorithm that we will see in the due course. Moreover, the asymptotical behavior, it also says that it represents a limiting behavior, and it works as a function of number, function of any other dependent variable that really provides some impact, that really has impact on the execution of the algorithm. And this analysis of algorithm helps us in many ways. First of all, we can analyze, if we analyze two algorithms for having for the same problem. For what I mean to say, suppose that I have a problem P and I have two solutions, A1, A2, and we both have we need to decide which one to be used. For that, if I write down the algorithm for method A1 and method A2, then if we analyze the time and space complexity of both these algorithms, then it will help us to decide which algorithm to use to solve that problem. That is the main perspective of the algorithm analysis or complexity analysis of algorithm. It helps the developer, or it helps the programmer to decide the best algorithm to solve a problem. In this video, we will focus on time complexity analysis of an algorithm, and space complexity analysis we will not continue, will not continue in this lecture. Later on, when we will find some problems and we'll analyze some examples, then we will go for discussing the space analysis. The asymptotic analysis of any algorithm is represented with the help of asymptotic notations. There are three asymptotic notations available for representing the time complexity of an algorithm. These notations are known as big O notation, omega notation, and theta notation. The big O notation, it is represented as big O, then within bracket a n. This n represents the size of the input, and this big O, it represents the upper bound of the time required to complete the algorithm. So what does actually mean? Suppose that we have plotted the time required with respect to the input size n, and normally, as this is the time required, this is time, and normally as n grows, this time increases, as the value of n increases, time also increases. But however, in certain cases, it is seen that we notice that sometimes for certain value of n, the time goes down, but all of a sudden, after certain value of n, the size of input, the graph starts growing like this. But however, it does not grow infinitely. So there is a limit up to what time it should go, or it can go. That is called the upper bound of the time required to complete the algorithm or complete the process. So that's why this upper bound, what is the maximum possible time required to complete the algorithm, that is represented with the help of the big O. Similarly, the omega notation, the omega represents the lower bound. It is also represented as a function of n, and it is given as omega then n, where n is the size of the input. It says that here we have seen that sometimes it goes down, but however it cannot go beyond certain time. So what is the what is the minimum time, not maximum, what is the minimum time required to complete the task? That is represented by the omega notation. And finally, the theta notation, this theta notation represents as theta of n. It provides an idea how much average time required to complete the algorithm. So these three notations, basically these are the three notations which are used in analyzing the time complexity of any algorithm. So we will see each of the notation in details, and whenever we we will also use some examples in order to see these notations, big O, omega, and theta notations. Now let us talk about the big O notation, which is represented as order of n, and where n is the size of the input. To understand the concept of order of n, or to understand the big O notation, let us suppose that we have an algorithm A, and this algorithm, we have plotted down the time complexity or time required to complete the algorithm with respect to the size of input n, and hypothetically assume that we got a curve of this type. So this is the curve that represents the relation between the time and the size of the input data. And this graph, if I say this time, this graph can be represented actually functionally in terms of n. If we assume that the time is equals to function of n, and if I say this is y and this is x, then certainly y is represented as function of x, where x is nothing but n, the size of the input data. Now we can see that this graph grows as and when the n, or the size of data, increases. But let us now consider another graph just above the given graph y. If I draw another graph just above this graph, or which will not cross, that is the y equals to f of x or y equals to f of n will not cross that new graph, then we can write down any graph randomly somewhere here. Suppose that this is the graph which represents y is equals to something like z of n or z of x. Then we can see that this graph y equals to f of n will never cross this graph y equal to g of n. So the big O notation of any algorithm also works in a similar way. So what we do here, big O notation of this algorithm, what we do, we try to find out another graph just above this given graph y equals to f of n, such that this y equals to f of n will never cross that graph. But however, this graph at this time, this point of time, at this state, y equals to gn, it is much above than that of the graph or that of the curve y equals to fn. But that is why it is not that much meaningful. So we can write down the same graph here. We can draw one more graph here, like somewhat like this. If I assume that this is the new gn, we do not consider this one. This is the better graph that represents the condition that y equals to f of n will never cross the function or the graph represented by g of n. So this g of n in general and hypothetically, this gn can be considered as the upper bound of the algorithm A, upper bound of A. That means the time required to complete the algorithm will never exceed the graph which is represented by gn. But practically, when we talk about the big O notation the upper bound of any algorithm, this is not exactly that we have represented just now. It represents a bit more mathematical way. It is more mathematically represented norms or form of the graph. So in reality, the function fn does not grow as we have seen just now. It grows somewhat like initially at the very initial stage, I mean with the low value of input data, or low value of n, it sometimes it goes slightly up, then it goes down. When after certain time it goes like this, it goes up, but it does not grow exponentially like this. It never grows like this. It grows up to certain value of time. Beyond that it will never go. Beyond that it will never go. Now with respect to the function y equals to f of n of this graph, if I wanted to find another graph g, what we can do, we do not care. Normally we do not care about the points up to here. The new graph may be started from here somewhere, and but however after certain value it should go above y equals to fn. So this becomes the fn. So if I write down, if we can draw one graph like this, or if we have a graph like this, then this gn can be a better candidate to represent the upper bound of the algorithm under consideration. There is a mathematical definition of the upper bound of any algorithm, or big O of n. That mathematical representation of big O n goes like this. If fn is the function that represents the time complexity of any algorithm, then we need to find any function g of n in such a way that if we multiply this gn with certain value, constant value c, then it always gives a greater or equal value with the function fn. So in that case, if we can find some function of gn that satisfies this condition, along with the fact that for certain value of n naught, this certain value of n naught means that if I see the function of fn, if we see the function gn, if we see the graph representing function gn, we can see here at this point, fn is bigger than gn. But however, beyond this point, beyond this value, and this value is considered as n naught, the initial starting point. Beyond that, when the value of n goes above n naught, for a value of n greater than n naught, the function gn is always higher than that of the function fn. So in that case, this gn is actually, the gn is considered as upper bound of the algorithm under consideration, that is the algorithm A in this case. A formal definition of big O notation may be like this. If fn is the time complexity of an algorithm A, then the function gn may represent the upper bound of the time complexity of A if there exist two constants c and n naught, where function fn is smaller than equals to c multiplied by gn for all values of n greater than n naught. And number two, the condition number two, both c and n naught are positive integers. When we represent the big O notation, or when we represent the upper bound of time complexity with big O notation, what we do, we write down the function fn as is equals to, function fn is equals to big O of c of gn. This is the way that we represent the upper bound of any time complexity of any algorithm for some value of c and n, where such that fn is smaller than equals to c multiplied by g of n for all n greater than equals to n naught. So n is the minimum point, the minima. N is the minimum point if it is, if we consider this one as fn, and n naught will be this area. Beyond this point, the value of fn will satisfy this condition. Now we will see few examples how to compute the upper bound of any algorithm, provided we have given the time complexity function fn. Let us take this example. This is an algorithm P1, and this algorithm has total 4 steps, and this is very simple, and it will basically take two inputs A and B. Then finally it will print result, and result is calculated in step 2.1 and 2.2. Step 1, it takes 1 unit time to complete this statement, and this is a loop. Step 2 is a loop. That loop will execute for n times. Here n is actually the size of data to be processed, and that determines mainly the total complexity of the time. And within the loop we have two statements, this statement number 2.1 and 2.2. So this statement takes 1 unit time, this statement takes 1 unit time, so altogether 2 unit times is being taken, and it executes for n number of times because of the loop. And here after coming of the loop, there is one more statement to print the result. So statement step 3, that is print result, that will take one more unit time for execution. So total this is 1 unit time. These are not within the loop, and within the loop we have two statements, and that's why total loop will be executed for n times, n multiplied by 2, because 2 unit time is taken, plus 2. This is the total time required in order to execute this algorithm P1. And now if I say that fn is the time complexity of the algorithm, then fn equals to 2 multiplied by n plus 2. This is the function that represents the time complexity. Now our goal is to find the upper bound upper bound of this time complexity, which we will denote it with the help of order of n, or order of the function fn. And now our main interest is to find a function gn. Let us first plot this function fn is equals to twice n plus 2. Fn equals to twice n plus 2 will look if I plot in x and y coordinates, then this is fn, this is fn, this is fn, this is fn is equals to twice n plus 2. And now our objective is to find a function, or find a graph which will actually after certain point will go above this fn, and that would be considered as the upper bound of this time complexity. Now let us suppose that as an example of gn, let me take 1 multiplied by n square. This is the function which is actually n square that varies with respect to n. And here we need to take a function g is equals to c multiplied by some function, so here c I am taking is equals to 1. It's a positive number, so that's absolutely fine to consider gn equals to n square, 1 into n square. So if I plot this n square, then n square will be here. This is the function, or this is the curve for gn equals to n square. Now n square, if I see that this is actually true here, n naught, because the condition was fn should be less than is equals to c multiplied by gn for some value c and n naught, where And when n exceeds is greater than n naught, here n naught here we can say this is the n naught, this is n naught, where this function n square is going above this function fn. So this may be considered as the initial point n naught, maybe 2.7 or whatever it is, and that becomes, actually this is true. So gn can be considered as, we can write down fn equals to big O of gn. We can write down fn equals to big O of gn, where gn equals to n square. But let me, if I see here this function, there is a huge gap between this function fn and gn, where gn is considered as n square. Now we have to find out the function gn such that it just go above this function fn, but not necessarily n square, because n square is going very high. And if I take another function gn, which is where gn is equals to gn equals to say 2n, let us say gn equals to 2n or 3n, gn equals to 2n or 3n, and this one will be the new gn. And this graph also, this curve also is considered, may be considered as the upper bound for the function time complexity that is denoted by fn, because all the points here, and maybe after some time going, it will go like this. After certain value of n, which is after certain value of n, it will go above fn. That means that can be considered as a upper bound. So out of these two functions, gn equals to n square and gn equals to twice n or thrice n, maybe say let us say 4n, maybe 4n. So if 4n is this function, then we can consider as gn is equals to 4n is a better choice to be the upper bound for this function. Okay, so that's why here in this case what we can do, we can take a function gn is equals to 4 of n, and that 4 of n will be the upper bound for this function fn, or the time complexity of this given algorithm p1. So we can write down here big O, this gn, big O of gn, where gn is equals to big O of 4 of n. And in practical, what we can do, we can ignore this constant term 4, and we can write down order of n. So if the function fn, the time complexity of the algorithm fn is equals to twice n plus 2, then we can represent this function, or we did a maximum, that is called the upper bound of this time complexity, may be represented with the help of order of n. So where it is, this is the big O of n. This is called the upper bound of the algorithm. Moreover, if I that is actually we should not take a function gn which is very high than that of the fn. It should just cross, or it just go above the function fn. So we have seen the example that if we take f equal to n square, it goes really very high above this function fn. So f n equals to n square, gn equals to n square is not the right choice. However, if I take order gn is equals to 4n or say 5n, then we can find out that we can see that this also goes above fn, it also goes above fn, and that would be the right choice for considering as the upper bound of that time complexity. Moreover, there are certain there are some tips to find out that function. What we can do, we have this here, fn is equals to twice of n plus 2. This is the function. So we need to find a function to twice n plus 2 is smaller than equals to some function. So that function can be taken as 2 plus 2 twice n plus this 2n, which is equals to 4n, less than equals to 4n. If I consider twice n plus 2 less than equals to 4n, and if I take this gn 4n is equals to gn, that would be sufficient to find out, that would be sufficient to be as a upper bound of this function. Moreover, we can test it. Let us say n is equals to, for n equals to 1, 2 into 2 plus 2, and less than equals to 4 into 1, which is equals to, this is 4, and this is also 6. 6 is less than equals to 4. This is not true, but if I take n equals to 2, then 2 into, oh sorry, this is 1 actually, 2 plus 1, 4. Okay, 4 is equals to 4. 4 is equals to 4. That means twice n plus 2 is less than equals to 4 of n for n is equals to 1, n equals to 1. So here we can write down that c is equals to 4 and n naught is equals to 1. So this becomes order of 4 of n, which is nothing but order of n. So this order of n, that way we can find out the upper bound of any algorithm. Again, let us take one more example. Suppose that the time complexity of any function, complexity of any algorithm, say P2, which is given as twice n square plus 3. Now we want to find any function gn. How to find it? So we need to find a function twice, which is n square plus 3. We need to find a function which is greater than or equal to the function 2n square plus 3n square. So this 3 will come here and we'll put n square here. That means less than equals to 5n square. And in that case, we can tell that c becomes 5 here. C equals to 5. And however, to find the value of n naught, what we need to do, for 2n square plus 3 is less than equals to 5n square, and if I put n equals to 1, n equals to 1, then this is 2 plus 3 5 less than equals to also 5. That means n is equals to 1 again here, and say it's okay, so n equals to 1. So here we can tell that gn, we can figure out that gn is equals to order of 5n square. That may be the right choice. G of n equals to order of 5n square would be the right choice to be used as a upper bound for the algorithm with the time complexity twice n square plus 3, where c is will be equals to 5 and n naught will be equals to 1. So that way we can find out the upper bound of any algorithm in terms of big O notation, and provided we have the time complexity function which is denoted by fn. Now let us see what is a lower bound or omega notation. Once again, let us assume that we have a time complexity function given as this function, and this is fn. By the lower bound, we mean that there is a function gn which will follow this trend. This is gn. That is, after certain point n naught, the gn will go below the function fn, and this function will never go or never cross this function fn. In that case, gn is known to be the lower bound of the computational complexity or time complexity of the algorithm being observed or examined. More formally, this lower bound can be defined as the function gn is considered as the lower bound of the time complexity of the algorithm whose time function is represented with function fn if and only if there exists some constant c and n naught such that for all n greater than equals to n naught, f of n is always greater than or equal to c multiplied by g of n. It implies that we have a function gn which limits or which shows the lower bound of time complexity, means the time complexity of that algorithm cannot go beyond this line or beyond this curve. And however, there must be certain point after which point this condition applies. But before that, maybe the function gn at like as this point, gn is smaller than that of the gn is higher than that of the function fn. However, after the point n naught, the function gn always is below the function fn. So that's why this gn is called the lower bound of the time complexity denoted by fn for the algorithm A. The last notation of complexity analysis is the theta notation. This notation gives an average bound of the time complexity. Again, for clarity or clear understanding of this term, let us assume that we have the time complexity function for a given algorithm as we have checked earlier. And now we have to find a function gn in such a way that if we multiply g1 with c1, then it gives the lower bound of this function fn. And if we multiply the same function gn with another constant c2, then this function gives the upper bound to this function. So here this is c2 gn and this is c1 into gn. Gn is said to be the average bound or average time bound for the algorithm under consideration. So more formally, gn is said to be the average bound or average time bound for the algorithm denoted by theta gn if there exists two constants c1 and c2 and also one more constant n naught such that fn is smaller than equals to c2 of gn and greater than or equal to c1 of gn. So in that case, gn is said to be the average time bound for the algorithm. So these are three notations. Big O notation, which gives us the upper bound of time. Omega notation, which gives the lower bound. And the theta notation, which provides with the idea of the average time bound of a given algorithm. So these three notations are used to analyze all the algorithms that we use to solve any problem in computation. So hopefully you have an idea of about all these three terms, and we'll not discuss examples for average and the lower bound. You can easily find with by taking as the reference of finding the reference that I have given in this video to compute the upper bound of any algorithm for a given function fn. So we can also find average and as well as the lower bound. Once we find both upper bound and the lower bound of time complexity for the given fn, then it is easier to find out average one. So that's all for this video. Thank you so much.